Okay, thank you so much. Thank you for your brief introduction about my career aspects and other things. I have also added some of my details that where currently I am serving and what my past jobs and what the other positions for the community, especially for the academia I'm serving on. The brief title of my topic will be the role of GNSS satellites, a generic name for global navigation and satellite system in natural hazards monitoring, because our country and specifically our Asian, South Asian continents and Asia are mostly vulnerable to these kind of natural hazards. So the high resolution GNSS satellite signals can help us to monitor, assess, and analyze the different uh, levels of uh, catastrophes at different altitude over the surface of the earth, so we can adequately and sophisticatedly monitor that if we have a strong ground and space-based systems for the monitoring and further forecasting. So it would be so helpful. So a little bit, I will talk about the GNSS, that what actually is GNSS, because GNSS is not only GPS, what we predict what we depicted from its name, that most of us deceived by its name that GPS is only GNSS, but it also consisted of different other satellites like GLONASS, Galileo, Baidu, and some other regional satellite system like QZSS and IRNSS from the Japanese and Indian countries, respectively. So these countries actually contributed most of the operation in the GNSS, because you can see that most of the satellites from the GPS, GLONASS, Galileo, and Baidu, despite Baidu has now 20 geostationary satellites providing quite uh, good pictures of the Earth and Earth atmosphere. So the different delays can be monitored with more accuracy and precision, particularly uh, in the context of the different hazards. For example, if we want to monitor the different man-made or natural hazards, so it can provide us a background about that how these signals generated at the ground, and then it's propagated and then evaluated to the upper layers of the atmosphere. So these are quite important. So right now there are certain LEO orbit satellites and geostationary orbit satellites that they can provide us quite freedom in monitoring the atmosphere and ionosphere at a lower altitude, where we can at least monitor these kind of things at and divided the delays at several intervals. So this, and by comparing these kind of things, we can have a good idea of what actually happening on the surface of the earth, and uh, how to forecast these. So as far as the GNSS satellite system is concerned, it is also operated with in situ satellites with the remote sensing. So most of the remote sensing satellites that are remotely operating and observing the Earth at different altitude, at different uh, orbital levels. So GNSS can also help and with in situ satellite system, and also provide a good background for those also. So if we roughly talk about that, what actually in the atmosphere, because we are remotely sense these kind of things with the GNSS and other remote sensing satellites. So right now you can see in this thing that we have a very closely compact layers of different atmospheric layers, and they are quite helpful for our aerospace, space, and avionics and aero vehicles, for the health of these, for its operations, and for its precisions in the data sets. These layers are quite important. to at least we have a know-how about what actually they are and how far it is from the surface of the earth. So principally speaking, we can have the lowermost layer. They are actually least in their distance from the surface of the earth, and they have very low space within between. So most of the weather balloons are our aeroplane services are cloud bursting, and these kind of activities happen in the lower atmosphere. But the uppermost layer that we roughly talk is ionosphere. They are quite important because it exists from 50 kilometer above the surface of the earth to up to 1000 kilometers, and they are giving us the very brief delays in our communication and our other aspects. So whenever actually uh, a disaster come from above the surface of the earth or below the surface of that, like for example in the case of natural hazards that we are talking later about these kind of things. So these delays are quite enhanced and pronouncedly enhanced during these kind of hazards. So after uh, taking good care of these delays and adequately measuring and quantifying what actually in these delays you can briefly and you can precisely monitor what actually going on the surface of that. Beside that, recently we have a race of big data in the form of AI. We are also working with such things, and they are also giving us very good clues about what actually going on the surface. For example, if we roughly talk a millimeter variation on the surface of the earth can be enhanced to hundreds of kilometers in the atmosphere because of the properties and of this media, that all everything what actually going on the surface of the earth, if it is propagated to atmosphere, it will be enhanced and its dia can be increased to hundreds of kilometers in the upper atmosphere. So these are quite important. And also there are several other factors like humidity, uh, wind pressures, and other different kind of things. They are also giving us a lot of information about what's going on. So all these satellites and their operations can significantly enhance the chances of different kind of things. Beside the weather forecasting and all other things, the natural hazards can be it would be a dream that at least we can forecast with these kind of satellite. So roughly talk about these coupling processes. This were some uh, there is a recent agility in this field that people are monitoring the ionosphere and atmosphere with quite different kind of satellites data, from remote sensing to different LEO orbits to GNSS and other operational systems. And also they are studying the mechanism of how these signals and these variations at any uh, natural hazards event, they how they are actually propagating to the lower atmosphere, followed by the upper atmosphere, and then to the ionosphere and exosphere. So these different layers are actually incorporated at different stages. And how you can see in this kind of this was one of a very brief paper published in the Journal of Geophysical Research Space Sciences editions, and they quite significantly and quite importantly show that how these plasma drift and how these ions are actually uh, propagated and how they are operating during a hazard time. So since they have different kind of nomenclature. Also, the Earth is also a very complicated planet with having a lot of different processes in its atmosphere, uh, its magnetic field, and several other kind of things. So, what actually not only the this paper defected the this paper defected the uh, they showed actually the ionosphere, but before ionosphere, different other processes like the ions drift, the recombinations of ions, the thermal anomalies happen. All these things actually happening in the lower atmosphere, and then they are actually pushing a drift toward the upper ionosphere and lower ionosphere, and then you can find out quite uh, different variations over the natural hazard region. So you can then find out what actually going on the surface of that. So this is somehow the University College London, they showed they recently they are also started this kind of work, and they depicted that how the energy is propagated to the ionosphere, and they significantly showed that these variations are not only concerned to the surface of the earth, but it is also propagated at several kind of things. But their defection is a little bit different because they showed a uniform slant going towards the ionosphere, but it's actually not like this. The natural hazards, whenever they're pushing the energy, they are propagated at several uh, different and several huge kilometers dia that they are pushing it towards. So whenever your satellites are operating at this certain area, so they are actually their signals are certainly delayed at different extents in the atmosphere and specifically ionosphere. So ionosphere delays can provide us information at different kind of things. Like for example, whenever you mathematical model these kind of things, they have significant outliers in the data sets. When we use statistically observe one thing, and when actually right now with the machine learning, when you process these large data sets, you can find out significant outliers in the data sets uh, at different kind of things. So you can find out that these couplings actually happening dually. Like for example, it can be from above, like from the sun, like solar storms and these kind of hazards are solar flares or other coronal mass ejections. They can also pause their energy, and they can also generate these kind of uh, anomalies in the ionosphere. On the other hand side, like our caustic gravity waves, they are also drifting towards the lower atmosphere and then upper ionosphere. So since these our natural hazards has also a huge amount of energy, so they are also pushing their energy and thus generated triggering these ionospheric anomalies, and we can significantly see it with the satellite data set. So these are very important. So if we talk about the background and the motivation that how actually my group started this kind of work, and we are monitoring the different kind of delays in the ionosphere and different atmospheric extents of the satellite data sets. So these are some of the things. Like for example, uh, different scientists from Russia, America, China, and different other countries, they actually work on these kind of things. They give us a little bit idea, the different kind of things. So taking this idea, different countries like France right now, China, they operate their own. They launch their own satellites for this purpose. Like the Demeter satellite was launched by the French government, and it's mean the detection of electromagnetic emissions from the earthquake regions. Its name actually depicted the specific region, like the Chinese CSES, Chinese seismoelectric satellites. So these satellites actually giving us idea, and they are only operating on the world most critical seismic zones of the world, so of the globe. So since they are flying over those regions, their signals are only limited to these regions. And whenever a natural hazards, because natural hazards are not not connected and bound to a specific a specific place, but at least by the ground seismology and other information, we can at least show that these are very uh, strong and seismoactive region. So these satellites have their orbital management, like they are flying over those region, and whenever a satellite and natural hazards come and occur, they operate in those regions and give us the delays over these regions. So these are some of the important things. So based upon these previous findings, we are actually so curious that how actually these ionospheric variations occur and how they are propagated at different regions. So we also took interest and started our studies, and this studies was quite important for our country also. So right now we are also working. We got many different stations, and we are now operating. Uh, Planning to start our course network throughout our country and our region to at least give us relief. Like Japanese government, they also have a lot of cluster. You can see the GNSS cluster across the different worlds. Right now, we are using the IGS data sets for for establishing this course network and establishing our benchmark studies that how actually these variations occurs and how we can correlate and monitor the data sets in future using these freely available data. But many countries have their dedicated and committed course network, like the US. You can find out the Australia, the Japanese government, and the different European regions, territories. You can find out. So they have the New Zealand peninsula. You can find out they have course network. But unfortunately, our Asian sector right now, China and some other countries are taking good part. But the Arabian Peninsula has lack of these kind of course networks because of I'm not sure what actually their policies and how they are working in this kind of thing. But this is a good idea to at least like Japanese government. Uh, they have now enhanced it to more than 2,000 continuous operating system stations, and they are giving us good idea, and their data is so refined and so real time that at least they can give you the early prediction very soon. At least they have the sufficient amount of course network. And also other countries are also, but maybe in future Japanese government will enhance the number of stations in these cars. So their course network is one of the important, and they have very precise data sets in this regard. So some of if my talk will be divided into several sections, I will roughly tell because my group is working on different kind of natural hazards like earthquake, tsunami, typhoon, and solar storm. So I divided my talk in different sections like the earthquakes because it's very common in my country, and everywhere it is creating devastation at different counties, at different levels, and different administrative regions. So this is quite horrible and quite worrisome for us people and for us, and we are strongly committed towards it, that at least we can work in this field. So if we talk about these kind of things, so earthquakes are one of the most important and most common hazards happening all over the world, and what actually the mechanism behind the occurrence of the earthquake. So it is actually abnormal amount of energy uh, saved at different plate boundaries, and whenever they find a weak zone, this energy abruptly comes out and become part of this atmosphere and also the thing. So this you showed that this is the real time predictions of of the earthquakes happen, and the ball size can show how much will be the magnitude and how big and large and small earthquakes are distributed at different regions. So the satellites can give you information about these kind of things. Yeah, so if we talk about the amount of energy, this we took from the British Geological Society. They actually show that how much energy is associated with an earthquake. For example, a 5 magnitude earthquake has an energy of 32 kiloton, and it is equal to the Nagasaki atomic bomb, which almost destroy all of the city. So if you talk that if you imagine that if we have a 7, 8, or 9 magnitude earthquake, so it is too much that at least uh, it has a it has an energy of more than several atomic bombs. So it is quite vulnerable and quite devastating. So at least we should think about this kind of. So this is one of our study that we recently did, and this earthquake happened in Pakistan, as the red star show. and it is noted by its by the neighboring country, even in UAE and Qatar, you can show, and Iran and different other countries, you can clearly show that there are several huge responses from the people over there, that at least they noted these kind of things. So what actually then we decided to study this earthquake, and we showed the different kind of things. Uh, um, Using the GNSS slant tech that is retrieved over the surface of the Earth from the continuous satellite data sets. So this is somehow the methodology we adopted, and we significantly found that within 5 to 6 days, 5 to 10 days, we have significant amount of energy released before this earthquake. And then we started to study that this is only the case study of a single earthquake. Well, what actually if we take these earthquakes in a cumulative amount? I mean, you can see in integration and more amount. So when we started study these kind of thing, a statistical analysis has been established, and they showed that the earthquakes with magnitude greater than 6 can significantly show some clues about the ionospheric and atmospheric disturbances, and they have also there is also contributions of storm events. Whenever we remove the storm events, you can find out that the peaks of these earthquakes before and after the earthquakes are quite prominent, and they show quite variations over the surface of the earth. So these kind of things are very important. This is furthermore we categorize the different things like the fault and fault mechanism of the different earthquake categories and different kind of things. Actually, it shows that these delays are quite enhanced. You can find out when we have a plane wave, but whenever it pass, the signal pass over the ionospheric irregularities, because they are quite enhanced at our mid-latitude regions and equatorial region. So they are quite significantly deteriorated, and whenever it is monitored at several monitoring stations, you can find out blatant and very clear variations in the signals of these GPS satellites and their signal. So apart from this, we also found out the different kind of anomalies happened, since I showed in in the previous slide that there are different mechanisms of how these plasma bubbles can variate the signals, like they can generate the positive and negative anomalies. They can also generate the pre, pro, post, and co-synchronized anomalies with the earthquakes and different kind of natural hazards. So this is recent. This is one of our recent study that my friend from Mexico did in Mexico, and they utilized the data sets from the Mexican course operating continuous operating system, and they depicted the machine learning algorithm like support vector machines, and they showed that the enhancement in the form of seismic in the case of seismic events are quite prominent with that of non-seismic event. And this diagram can show that how much events we studied, and the number of events showed that the seismic activities uh, contributed more energy to the atmosphere, to the ionosphere, than the non-seismic region. So these are quite prominent and quite significant in the aspects of, and it supports our hypothesis that at least this coupling can be, of course, real, and it can help us one day that at least we can give good idea of what going on in on the surface of the earth during the um, natural hazards. So these are quite important. This is a also our recent study, and this is the course operating stations that we actually utilize our own data sets. This is the devastations of this earthquake, and it is recently published. It happened in 2019 in Pakistan. The earthquake uh, caused several casualties of lives, and a lot of threats and a lot of devastations uh, to the infrastructure of the country and this territory. So we got very significant variations in the atmosphere, in the ionosphere, and on the ground. It was supported by one of another friend. They are working in another organizations, and then they got some data sets from they retrieve some data sets from the ground station, and they exactly show the same anomalies that what actually we showed in the ionosphere, in the form of spatial variation, in the form of temporal variations, and how they were enhanced during the earthquake days and before the earthquake, even on the surface of the earth. So the ground station also give us a clue that at least yes, some things were happening, and it is not a systematic way that the earthquake energy is propagated at a single point on a single day, from the ground to the surface, uh, to the atmosphere, and then ionosphere. It is at least a process of several days. You can find out that before the earthquake days here somehow the earthquakes occurred, and you can find out here somehow the earthquake occurs, and the ground variations were happening several days before. But after several days, the earthquake anomalies were significantly contributed to the atmosphere and ionosphere. They were quite clear in our analysis, and it is available online, and you can. So this is another in situ satellites that beside the GNSS tech and the GNSS total electron content, we have some other in situ satellites like this was uh, uh, the Demeter satellite launched by the French government, and it is, as I mentioned before, it is only dedicated to these kind of variations emitted with the earthquake energies and generated with the earthquake energies. So they have particular importance, and we studied one earthquake in the southern America, and it showed quite clear variation that this signal that these flights near the epicentral regions and earthquake breed regions, they show quite significant variations at the regions before the earthquake, and these kind of things were quite prominent in the satellite data sets. So this was the model comparison by one of the Taiwanese scientists, because they were also so suffer from this different earthquake region, and they showed quite different variation. And you can find out that our variations on the earthquake day were quite synchronized with the model, because this model showed that at minus 30 degree and plus 30 degree, 20 to 30 degree, the ionospheric variations are quite enhanced. And when we started studies the real-time data set, we find out that at the same region our anomalies also quite prominent from the rest of the days. You can find out there is no such substantial variation over the surface of the Earth from the GNSS satellites, from the different other satellites. But when on the earthquake day we found out the variations, and the model, this was the model that is operated by the NASA, and it showed quite synchronized variation and collocated over the surface of the earth for both the things. So it also gave us quite confidence, and also give us a lot of information that at least the model depicted and model clear our variations that it happened. So this is the next step of our study, that how we are actually operating the different um, uh, ionospheric variations with the GNSS satellites during the storm time event. So this was one of the storm events that happened uh, before 2020, and it is also published by one of my colleague, and they also showed that the different kind of variation happened during the storm event. So you can find that the storm has a for several events like the sudden storm commencement, the initial phase, the main phase, and the different kind of thing. And different variations are associated with the uh, different layers and the different phases of the storm. And it is also quite prominent that the storms can be classified by the different generation mechanism like the solar flares or the coronal mass ejection or any other kind of thing. So it is also quite prominent that with the GNSS satellites, at least we can predict that what is the source of these kind of storms and how they are actually triggering and how they are coupling with the magnetosphere and then the ionosphere. So we also have a clear idea about this kind of thing. So this is somehow the interactions of the storms with the Earth and itself. You can find out that they can also variate the IMF coupling due on the polar regions. They can also variate the prompt penetration electric field or dynamo electric field, and they have also variate the plasma direction during the storm event. So these are some of the quite prominent properties that at least with the GNSS satellites we can study these kind of things, and we can also study these different kind of drivers that actually associated with the storm, and as a response of these, how they are creating the different delays in the atmosphere and ionosphere. We can have clear idea about these kind of things. So this is one of our study that we did in the South American, and there we utilize their continuous operating stations that are 24 by 7 working, and how and they have a very good uh, distance from the magnetic equator, and we took the data and showed how these variations can be associated with the different sudden storm commencement and how they are and also they variate at the strength of the different phases in the storm. So you can find out that with the after the sudden storm commencement in the storm, the variation quite enhanced from the abnormal from the other way, and it is quite prominent, like you can see, but it is quite prominent that somehow it is a positive variation, and it is significantly beyond the upper bound, and somehow it is in the form of negative anomaly, and they are suppressed towards the negative zone below the some average level. So this has some different mechanism, like for example, maybe these stations located at a time zone when the plasma drift occur, and when the equatorial plasma bubble change its direction from east to west or west to east, so then they are suppressed towards the negative things, and on the other hand, if they are enhanced, so these signals and these satellites were in the direct way of these equatorial plasma bubbles, and then they enhance towards the positive levels, and quite significant to outliers can be happened beyond the mean line or at any bench value or bench line. So these are quite important study, and this give us very good idea and good motivation that at least our variations were quite clear and how they are associated with the different storm events. So these were the magnetometers data sets that they are actually measuring the Earth magnetic field during the storm events, and it's also supported uh, our anomalous pattern in the ionosphere from the GNSS satellite system, that at the equator regions these variations. This is the southern storm commencement, like this figure, and then it is quite enhanced after the storm days during the initial, final, and the other kind of days. So this is also the spatial pattern that we took from the GNSS satellite system, and you can find out that before the storm, there is no such responses in the ionosphere, but after storm they have significant storm pattern and storm responses. But it also depends that on the western side of these South American regions, there are no quite clear variation, but in the middle of somehow middle regions and the eastern coast of the South American continent, the variations enhance after the storm sudden commencement. So these kind of things. And this is also supported by some other satellites, like for example, the thermospheric patterns from the swarm satellite and Gooby satellite. They also show that these variations actually propagated from ionosphere to the thermosphere. So whenever we have such so much evidences, we were quite prominent that you can find out that these were so clear variations from the swarm satellites in the thermospheric. So not only the ionosphere is affected during the storm events, thermosphere has quite clear variations, and they are also varied in the perspective or in the context of the storm responses. So they have clear variations at the different local time and variation with these kind of things. So another aspects and another point of our my presentation is that we can even cyclone monitoring system, and they are also working good with the GNSS things, and can also GNSS can also track the path and the pattern of the different cyclone thing. Like for example, the cyclone Asna that recently hit the Arabian Sea near the India and Pakistan border, and you can find out the pattern and the intensity of this storm, that how it is propagated from the oceanic part to the terrestrial part, and how they have actually varied its pressure, air pressure, and the different kind of thing. So when we study the GNSS data sets, it shows that on the same tracking regions, they have significant variation, and you can find out that at certain regions it exactly match with where the pressures and the intensity of the storm core enhanced are depleted at some region. So this also gives us another aspect of the GNSS monitoring with a different kind of thing. Volcano mapping is also quite in, and it is also give us a good idea of how we can monitor the volcano with the GNSS signal. So this was one of my recent study that we did uh, in 2017, and we got quite important things that the plume height and even the plume extensions were quite clear in the temperature events, and then the nearest GNSS stations, they also show quite clear variation that whenever the film excavated and they were evolved to the ionosphere, the ionosphere delays were quite enhanced during these kind of the event. So it is quite prominent that we studied these kind of ionospheric events in quite strong conditions, because ionosphere is mostly vulnerable and it has significant variation from storms and solar activities. But at least these kind of events uh, were studied, and these all these information were gathered during the quiet storm conditions, and during these quiet storm conditions we have clear ideas of how the ground and the satellite data sets varied at different extent over the system. So this is all actually from my side, a little bit briefing and these kind of things. This how actually we are working in propagating and preaching these kind of knowledge in the national level. Then I have several international collaborations and several and part of different organizations like the COSPAs, like the IAGJSG1, and the different other events and different other university visits and different kind of things, where we are actually participating and propagating and preaching these kind of knowledge and taught at different levels, from the to the students to policy makers and different kind of thing. A little bit my contributions to the scientific community in the form of the different journals editorial board, and they are quite important in our field, and their issues are now open. Everybody is welcome to submit and work in this kind of thing. So some of the prominent papers from my group at Institute of Space Technology that we are working on. So I highlighted some, and some are not highlighted, but at least they have, yeah, they are included in these lists. So you can find out in the list how much paper we have and what actually my achievement, that at certain level we got the different kind of things during my postdoc in KMITL Thailand. I got the gold medal there. and then the community services, like I mentioned, the different EGU convenieurship, the GGOS, and the different kind of thing. The COSPAR Young Researcher Award that I recently got while publishing significant paper in the early careers and the book chapters. I have several, but this is actually related to this topic and this thing. So this is all from my side, and you can also reach me at my email. Here I mention it. Uh, and thank you so much from my side.